So anyway, I'm going to go ahead and record the lesson today so that people that are not here right now have a shot at it. And anyway, so what we're going to do is we've got this circle right here. Now, again, the reason you'll notice that I drew it this way is I was trying to give it the illusion of three-dimensionality. You follow? Does that look vaguely 3D? Yeah. It looks vaguely 3D. We've got all these squares popping out. Now, what happens, generally speaking, what people want you to do is kind of get an idea and literally draw one of those pieces like we would with a Riemann sum and think about what that piece would be. So if you're looking at this piece right here and we broke it out like this, it would look something like that, wouldn't it? So we'd have this square that's right in here. And as it slides along, this is what we had talked about. We were going to slide along perpendicular to the x-axis, which means all of these little pieces, if I were to draw them in and try to make them look a little 3D, would come along like this. And those would be a little dx's, wouldn't they? Since it's perpendicular to the x-axis, the thickness of each one of those boxes, because what we're doing, remember when we first did area, how we filled it up with little rectangles? Well, couldn't we make a shape by filling it up with little blocks of wood of various sizes and stack them all together? So that's what we're going to do. So we've got this dx, but from here to here, we talked about that was 2y. This one is also 2y. So the area of this piece right here would be what?
Hey, Mr. Kenner?
Yes.
You posted practice volumes of known areas. I think you're doing the one without the known areas.
Okay, this was from last time. This is just a repeat of what we had last week. Let me go ahead and let me see what I can do here. Back to our video. Okay, so what we're going to do is we're going to look at this piece. So I'm stacking these little rectangular solids in there. You guys follow that? It's actually called a rectangular prism, and you can imagine doing that. In fact, to the point where I saw them once, it was really, really cool. You guys ever heard of like how they'll take like a skull and try to recreate what a face might look like? Well, they did this, which is really amazing because it's really the same concept right here, where they actually built this because it was too damaged. They actually had, by stacking little pieces of paper, they built the whole skull out of pieces of paper. Now, what would be the benefit of doing pieces of paper, like just one after another of various radii, moving up with all of those pieces? Think about how chunky this is as I drew it. What would happen if you did it with pieces of paper? It'd be very, very smooth, wouldn't it? Because those dx's would be so tiny, it would just be really, and then they were able to put clay on the face and they just made that face absolutely pop. It was perfect. And they were able to identify who that person was. So this is actually used in certain circumstances. And so the thinner this is, the more accurate it would be. But here's the deal. Do you guys follow that this right here is 2y? Do you guys understand why that's the case? From here to here, this is the y-axis, is y. So this is also y, so that is 2y. I said it's a square, so if this is 2y, then so is this, also 2y. So what is the volume of that piece of the box? Careful. It's 4y squared dx. Now, this is what happens, everybody. I've actually always thought, man, that's like bad math. Do you see what's bad about this right here? I've got a disagreement in variables, don't I? I'm going to actually integrate because I don't just want one of those things. I want all of them, don't I? So what I want to do is I want to integrate how that works, but I've got a disagreement in variables. I'll fix the balance here in a moment. But what is y squared? Well, it was a circle, and we know that x squared plus y squared is 25. So what is y squared? Isn't that 25 minus x squared? Oh, by the way, can I pull the 4 out in front? So I could pull the 4 in front, and I could change the bounds to 25 minus x squared dx. Now, the thing is if you look at this, what are we doing for x? What does x vary from and to according to this picture? X would start, look at the picture. The furthest left it would be -5. What's the furthest to the right would it be? +5. So my bounds of integration, hold on, would be -5 to +5, wouldn't they? But let's use some symmetry. What would be smarter? Shouldn't I do 0 to 5 and then double it because both sides are the same? Now, why is it super nice if you can ever bring 0 into your stories? This makes it easier, doesn't it? So we're going to go ahead and do 0 to 5, but then we're going to double that answer. So we really have 8 of those. And so what we have just done is we've created this situation where we've got 8. We're going to we're going to take the antiderivative here. This is what we've got. We're going to go from x equals 0 to x equals 5. And we didn't just find something. We found literally the perfect volume of this shape. And how thick would these things be since we're doing this integration with a dx? We're making them infinitely thin. And so we're making the perfect volume of 666 2/3. And this was done in inches, and this would be cubic inches. What do you guys think so far? Kind of cool. Now, here's what I'd like you guys to do, is I would like you to go to your Google Classroom, and could you please open up the week that was labeled March 19th, 15 and 19. So I'm going to go ahead and share this so you can see what I'm going to do here. So I'm going to go in here to the week that is March 15 to 19. I guess I need to move this across and then I'll do a reshare. This is always fun to do all these things. So I think this is the right place. So I did something for you right here. You'll notice this little GeoGebra link right here. Let's grab that thing. And let's open a new tab here and let's paste it in there and let's see what happens if we take a look at this thing. Now, what this is giving us is somebody has generated really, really honestly amazing program. I'll give you a second. You don't have one? Bummer. Okay, you can follow along, you can watch. But the cool thing is that we can do this. So the thing is the curve that I gave you was actually x squared plus y squared equals 25, right? But if x squared plus y squared equals 25, then what is y itself? Is the square root of 25 minus x squared. So I'm going to come into here and I'm going to change this to 25 minus x squared. You guys okay so far? I just isolated x squared plus y squared equals 25 for y. Now for the bottom curve, I'm going to change this to minus the square root. Now, why is there a minus there? Because what happens when you take the square root of both sides? You get a plus or minus. So we got the high side on one, the low side on the other. Now, the upper and lower bounds. Now, interestingly enough, I wish you guys had a mouse. It'd be a lot easier. But if you hover your mouse or your cursor over here, you can zoom in so you can see it a little bit better. But I want my upper bound to be 5, and I want my lower bound to be -5. So if you guys have a better quality computer at home, you can play with these things and make them what you want, okay? So I now have, and I'm going to hit clear traces so I can see it. Now I've got a little better story. And what I'm going to do is one more thing, should be good. Right up here at the top, it gives me options. Whoever designed this was just an absolute, this is so cool. I can choose any kind of cross sections that I want. And as it turns out, the one that they picked first, the far left will be squares. They have squares, they have circles, and a bunch of different things that are here. I'm going to move this all the way to the left so you can see it hit clear traces. And now if I slide this thing along, what it's going to do is it's going to give us a visual of the shape that we just talked about. It is a little herky-jerky, so as you draw that along, if you're fast, it'll miss a couple of them for whatever reason. So if you go really slow, you can see that there's one of them that got missed right in here somewhere. But this is the shape we just found the volume of. That's 666 2/3. And even better, if you are at home and you have an actual mouse, you can actually grab this thing and start pivoting it. And you could look at it in different, you see how you can look at it in 3 dimensions. This is just a solid that you just created. The only thing that's a bummer about it is once you start jacking with it, it's really hard to get it back. But what you can do over here, let's bring this all the way back. You can also play with it by saying, well, I want more or I want, say, less increments. So that thing was 10 units across, right? From -5 to +5. If I told it that I wanted to do increments of 1, then as a Riemann sum, how many would I get? I would just have 10 little pieces. And so as I drag this along, it's not going to be nearly as perfect as the one I just did because it's just going to show you these different pieces. But that's a really beautiful visual that I love that you guys can have. What do you guys think? Is that pretty doable? So that gives us an idea. So let's go ahead and go back here to this and let's try another shape, but keep that thing out because we'll use it again. The base of the solid is the region enclosed by a circle centered at the origin of radius 3. So almost the same thing. So what is the master equation that would make a circle of radius 3, everybody? That would be x squared plus y squared equals 9. So I'm going to write that up here. X squared plus y squared is 9, or in other words, y equals plus or minus the square root of 9 minus x squared. You guys okay with that? Very much like the problem we just did. It says we want to find the volume of the solid if all the cross sections perpendicular to the x-axis are equilateral triangles. So here we go. I'm going to, again, attempt to do some art here. So here's my x-axis, my y-axis. Here is my little circle coming in here. What's its radius? It said 3. So it's here like this. That's 3, 3, 3, and 3. And we've got our z-axis coming out of the page right in here, and we're going to stack equilateral triangles like this. Now again, if your equilateral triangles suck, I don't care, it's all good. It's not going to be that big of a deal if your picture isn't great because we have some technology that's going to help us do that. So, are you guys okay with that? So what I would love to see you guys do, so what we're going to do is we're going to break this thing out and just draw it right here. And we're going to make it look sort of 3D. This is kind of the important thing that you do because although this picture may suck, as long as this picture is good, we're golden. So it says we're going to go perpendicular to the x-axis. So they're going to be like this. So guys, is this a dx or a dy? I'm sliding along that axis. Each of them as I stack, it's going to be its thickness coming this way. So it's going to be a dx, right? So see if you guys can help me what this is. From the base, what is that base? All the way across, just like the previous problem. It's 2y. Now, what kind of triangle is this thing? That's equilateral. And if it's equilateral, then we know that all of those angles are 60 degrees, right? So this is a special right triangle, isn't it? And if it is a special right triangle, then this is 60 degrees. This is also 2y up here, isn't it? So how can I figure out the actual height of that triangle? See if you guys can remember your special right triangles from analysis and math 2. If this is 2y, what's this piece right here? Y. And that makes this piece right here y root 3. Okay? Remember the whole square root of 3 that popped in special right triangle. So what is the volume of that triangular prism? That's what that's called, by the way. This is a triangular prism. How do you find the area of the front face? Base times height divided by 2. So we have base, 2y, times the height, y root 3, divided by 2. Is that volume yet? Times dx, you got it. Because now I've got the area of that front face times its thickness, right? And then what do I want to do? Is I want to integrate that, don't I? Why? Because I don't want just that one. What do I want? I want all of them. And where do I want it to go from, and where do I want it to go to? I want it to go all the way from -3 to +3, or 0 to 3 and double it, right? Which is what I'm going to do. Let's go ahead and do that. Let's go 0 to 3 and let's put a double in front. But let's clean it up a little bit. Let's clean it up a little bit. Can I kill these two 2's right there? What's another thing that I could do to make life a little bit better? Is there a constant sitting in there? Isn't that root 3 sitting right there? Couldn't that root 3 therefore come in front? Because we could do that with all constants. So I got 2 roots of 3 there. And what's left inside? I took everything out. The only thing that is left inside is y squared, isn't it? But let's look up here. What was y squared? 9 minus x squared dx. Well, have we done a lot harder integrals than that one? We certainly have. This is pretty simple, straightforward stuff right here. As it turns out, if you do this correctly, I think you just get 10/3. So because you guys know how to integrate basic problems like this, I'm not going to take the class time to have you literally plug those things in one at a time. So what's the actual volume of this thing? Isn't that 20 roots of 3 over 3? Now, again, just to show that we can, let's go ahead and take a look at that computer program again. Let's see what happens if we pull up this computer program again, because I wanted you guys to see how to do that. So what was the bounds that we had? It's no longer 25 minus x squared. What is it? It's just 9. It's 9 minus x squared on both sides. And the upper and lower bounds, how big and how small can x be? It's going to go from what to what? It's going to go from +3. This is the one criticism I would say. They should put lower bound first and upper bound second. I screw that up myself when I use this. Often I put it in the wrong order. But there's something else that happened. It doesn't say to use squares this time. What are we using instead? Equilateral triangles. So if you go up here to the top, you can slide this along. We've got squares. Slide it over, not a semicircle. There it is. We want an equilateral triangle, okay? Pretty awesome programming that somebody did to make these easy for us. So this looks bad, doesn't it? Look at the picture. It looks awful. What do I need to do? I'm going to clear the traces. You guys follow me? Just how the program works is they have all this evidence. And if we want a decent looking model, we've got a total of 6 units across. How many increments would you guys like to see? How often should I put one? What's that? One every one? That's super chunky, but okay. One every one? I could do that. I'm going to zoom in a little bit because this one's going to be smaller, but as I come along, come on. It's pretty good. Do you have a pretty good feel for what it looks like? But, sometimes it helps to kind of move it around so you can see it at different angles. So it looks kind of like a dunce cap, doesn't it? I don't know if you've ever seen something like that, but it looks kind of like a dunce cap. And of course, what could you do to make your approximative method better? Just more increments. You could say, well, you know what? It's not really that big. My calculator can do that. How about every 0.1? So now as I slide along, it's going to do a whole lot of those things. And as it turns out, if you slide it back and forth, you'll pick up some of the ones that it missed. But how accurate is this going to be if I slide it that way? Almost looks like what you'd make out of a 3D printer, doesn't it? Has that kind of shape to it. And then we could rotate it and you can see a little bit more clearly what it looks like. What do you guys think? Is this visual helpful? I mean, to me, it was. When I was in college, we didn't have any of that. It was just sort of like, they told us and they were like, there you go. Now find it. And I'm like, I don't even know what it looks like. I couldn't do it. So anyway, so what do you guys think? And I don't know if you caught that. This program is pretty stinking cool because you'll notice down at the bottom, what else did it do? It actually tells you the answers, which I'm almost not a fan of, that it actually does that far, that it gives you everything. So we just did 2 circles. Of course, now everything is not going to be a circle. That would be silly if everything that we did ever was always just a simple circle. So we're going to do something that is not a circle now. We're going to move on to a new shape. So we have a mathematician that has decided to make a paperweight. And if you're going to make a paperweight, and you can, why not make it out of something that is a little bit more significant than a simple circle? Let's go with a sine wave. So we've got one piece of this sine wave, and that 2 right out in front is going to allow us to make the amplitude a little bit bigger. So again, let's try our best to make this thing look 3D. And so it's going to look something like this. Now, you guys should remember from pre-calc that, long time ago, that a sine wave gets its job done in 2 pi, right? So it says it only wants one arch of that curve. So where am I going to stop it? At pi itself. So that's what we've got. And each cross section perpendicular to the x-axis, notice we're doing that again, same idea, is this piece right here, perpendicular to the x-axis, like that, is going to be a semicircle. So again, I'll try to make it look okay. It looks about like that. Looks like a taco, like a hard shell taco maybe. So I've got that little thing and I'm going to slide that along. So are you guys okay with that? Now I'll show you, we'll do the visual in that program in a moment, but for now, is that okay? So is this a dx or is this a dy? Well, the hint is it says perpendicular to the x-axis, it will always be a dx. If it says perpendicular to the y-axis, it's going to be a dy. So far we're playing dx's. And what is the formula for this shape? What is the area of that weird little shape? It's semicircle, pi r squared divided by 2. So we've got this 1/2 pi r squared, right? But of course, we don't want area, we want volume. So we're going to end up with the volume is going to be 1/2 pi r squared dx. But, so let's look at the picture though. What is this distance from here to here according to the mathematics? Isn't that just y? Do you guys buy that that's y? From here to here is the y value, isn't it? But what is y? Y is 2 sine, but in terms of the circle, what is y? It's the diameter, isn't it? So y is the diameter of the circle, right? Now you don't need to write all this out. It's just, this is the thoughts that I'm going through. Since y is the diameter, how do I turn it into the radius? I need to divide it by 2. So what I would have then is I have 1/2 pi, and instead of writing r squared, what would I put in there? y over 2. Sine of x over 2. So what have I just got? Have I gotten better in terms of what I want? I should, shouldn't I? So there's a few things that I could do here. And the first of those things, I feel like I have something. Oh, there was supposed to be a 2 sine x, wasn't it? Yeah, it was a 2 sine x over 2, which is probably why I picked that 2 there in the first place. So it would just come out okay. And so I guess these are going to cancel. And so we've got a 1/2 pi out in front, and it is a sine squared x dx from where to where? 0 to pi. Now, this problem right here in and of itself doesn't sound that bad, but I will tell you, we actually have never yet actually integrated sine squared. I have never made you do that. Because as it turns out, that's a little bit boogery to do at first glance. It just is. But it's not as bad as you might think. So why is that hard? It's because there's a chain rule playing there, isn't it? This is the sine of x quantities squared, isn't it? So as it turns out, like if you try u substitution to do that, like what would you call u if it was sine squared? You call it sine. You have to, because it's definitely what we'd consider a composite function. You call it the sine, but then the derivative of sine is cosine, and I don't have that. So I'm like, u sub doesn't work. Interestingly enough, what you can do is you can go back in time to math analysis. Sorry, pre-calc, here we go again. There's a little identity that says the cosine of 2x is 1 minus 2 sine squareds. That's an identity. It's on your card that some of you still have lodged in the front of your calculator. Could you guys help me isolate this sine squared right here? So wouldn't it be negative 1 plus cosine of 2x is negative 2 sine squareds? So now what? Oh, so we have this 1/2 pi. And now we have, if we're dividing both sides by negative 2, we have 1/2 plus, actually it's minus, isn't it? Because we're going to subtract, minus 1/2 the cosine of 2x dx, x going from 0 to pi. Now I know that that feels a little bit awkward, but bear with, because you didn't know how to integrate that, but I think you guys know how to integrate that. What's the integral of a cosine? Just a sine, right? Pluses and minuses, we'll figure that out in a second. But we have a chain rule, there's a 2x in front, right? So normally when you do the derivative of that, you get a multiply by 2, but this is an antiderivative, so we're going to divide by 2. And so we're good to go. We have got 1/2 pi. What's the integral of 1/2? 1/2 x. The integral of a negative cosine, be careful about this, should be a negative sine. But careful, this is an antiderivative, right? So what's going to happen when we do this? We still have that 1/2 in front, but then we also then have to deal with the 2x that was sitting in here. So what's it going to be? I believe it's 1/4. Because we already had a 1/2 in front, didn't we? We already had a 1/2 in front. And we're going to do this from 0 to pi. And that should do that pretty nice. And as it just so happens, when you go to plug this thing in, something kind of cool happens. When you plug in pi, before I do the problem, what is the sine of 2 pi? Picture what the sine looks like. The sine of 2 pi is 0, isn't it? What is the sine of 0? 0. Also 0. So as it turns out, when you plug in the upper bound, this part disappears. When you plug in the lower bound, this part disappears. So really we have this 1/2 pi, and we're going to plug in pi here. And then we're going to, I guess I'll write it, minus 0, and then we plug in 0 here, and we get half of 0 minus 0. Gee, most everything is gone. What is the area, or the, excuse me, the volume of that piece? Is a half pi times a half pi. That's pi squared over 4. What a strange answer. But that is, in fact, my volume. So let's go back to that little program. Again, I don't know if this is helpful to you to see that, but I felt like when I was in your shoes, just the ability to look at it really helped me a lot. So I'm going to go ahead and take a look back at our little program that I showed you. And we're going to change our bounds. So what is the top curve? 2 sine x. Let's go into here and make this 2 sine x. Our bottom curve is 0. They didn't actually give me anything there. So we just have 0 itself. What is the lower bound? Where does our integral start? It should have been what? 0. The top of our curve was pi, which I believe on this one we can just type pi. If not, we'll just guess at 3.14. It took it. I haven't done that in a while. And then what shape, because it's not equilateral triangles, what is it supposed to be? Semicircle. So let's see. Oh, there it is. There's a semicircle. And I'm going to pull this all the way across so I can get there. I'm going to clear my traces so it'll only show me the portion that I'm interested in. This isn't going to be a very big region, so I'm going to zoom in a little bit. And if we drag that across, this is the cool shape that is our paperweight. Don't you wish you could have this paperweight? Kind of a cool paperweight. It's kind of neat, isn't it? So bizarre that you can go 3-dimensional with this thing. And I can actually show you how to build what this person did, because actually who made this little applet right here is actually just using what's already buried inside of this program called GeoGebra. It has this ability to do this built in. This person just made it a little bit easier for us to build without knowing some of that substructure. Okay, so I'm going to pause there for a moment, and I would like you. What's our shape? It says an isosceles triangle, right? So it's going to come kind of like this. I'm trying to give you that illusion of 3-dimensionality here. So some kind of shape this way. Hopefully that makes sense. It's kind of coming out of the page a little bit. What's this value right here, everybody? That's y, isn't it? What's this value right here? Y as well. dx or dy? It's definitely a dx. What's the area? What's the volume then of that little wedge that I drew? What's that? Y squared divided by 2, because it's a triangle. So we have 1/2 y squared dx, right? So what about that? So we need to get rid of this, don't we? So guys, how am I going to get y squared? Well, unfortunately, that's the one part of this problem. The setup is actually fairly simple. And what are we going to allow x to go from and to? 0 to 2, right? Could I use symmetry on this? Well, I might be able to, but I don't really think it would be wise. Those are pretty easy bounds. The bummer is what is y squared? So off to the side here, let's figure out what is y squared. Well, that would be 2x to the half plus, oh, no, minus, just kidding, minus x to the 3/2 times itself. What do you think? Is that going to be easy to do? Eh, it's not as bad as you think. Let's start going for it. What's 2x to the half times 2x to the half? Just 4x. That's not so bad. I'm going to start writing it over here as we get it. 0 to 2. That's just plain old 4x. Okay. Now, if you didn't catch that, remember when you multiply things, what do you do to their exponents? Add them. So you got a half plus a half, which is 1. What would this give you right here? That'd be negative 2x to the 2. Negative 2x squared. Good. What about this part right here? Same thing. Oh, so if this is negative 2x squared and this is also negative 2x squared, then what do we have? So this problem looked like it was going to be a beast, and actually it's not being that bad. What's the only thing I haven't dealt with? I haven't done the very, very last one. So what is negative x to the 3 halves times negative x to the 3 halves? Positive x cubed. And that, ladies and gentlemen, is about as nice of as an integral as you're going to see, isn't it? Pretty nice. So let's go ahead and set this one up. What would be the integral of 4x? So just, I want to do some of those so we don't forget how to do them. Integral of 4x, 2x squared. Cool. Integral of negative 4x squared. Negative 4/3 x cubed. And x to the 4th times 1/4. You got it. And what's really nice is this goes from x equals 0 to 2. And don't we love it when someone's nice to us and gives us 0 as a bound like that? Because this time 0 just killed everything, didn't it? So what's the only thing you have to do? Plug in 2. That's awesome. Turns out, when you plug in the number 2, pretty nice little things happen because 2 squared is 4 times 2 is 8. This kind of canceled most of that out anyway. This part is just 4/3. You can believe me on that if you want to. So what's the actual volume of this crazy little shape? Just 2/3. Isn't that weird? That you know, pretty nice answer for such an obnoxious. And this, by the way, would be units cubed. So what I think I'd like to do is I just have a couple more shapes to go right here. So what we have is in number 5, there's an elliptical region. So notice in this case, your x squared and your y squared have a slightly different feel. So, you know, when you draw that region, as I recall going back to our days in that class, we would end up having the x's go over and back to 2. The y's would actually go, I got to be a little bit careful about this, go as far up and down as 3 and negative 3. That's kind of the shape of it. And they're saying, again, isosceles triangles with a hypotenuse on the base, cross sections perpendicular to the x-axis. So you're going to be coming in like this, where you're going to have this triangle like that. Maybe it'd be helpful to actually look at this one. I was going to have you do it, but I'll just get it started for you. So if I were to take this triangle, which looks really ugly to me, sorry. When you draw a right triangle but it's hovering, the angle doesn't look like a 90, even though it is. So if I were to bring this thing over, here's my triangle. This is what? According to the triangle, what is that? Isn't that the hypotenuse? So what does that make this right here? Is it makes that right there 2y? Because from here to here was y, here to here is y. How in an isosceles right triangle, this is a 45, 45, 90. We're doing a lot of special right triangles today. Square root of 2, yeah. We're going to do 2y divided by root 2, aren't we? Whatever the hypotenuse is divided by root 2 is how you go to get the sides of a 45, 45, 90. What's that make this guy right here? The same thing. So the volume of this little wedge, it's going to have our dx there, isn't it? What happens if you multiply those two together? What is 2y times 2y root 2 root 2? That'd be 4y squared over 2, so just 2y squareds. Oh. But just like the previous problem, we have a little bit of an issue because it doesn't agree, right? But we did this a little bit back in our U sub days. What do you want then? What is 2y squared? The equation says 4y squared is all that stuff, so what's 2y squared? Half of it. Sweet. So the volume is 1/2 of 36 minus 9x squared dx from what to what? What does x do? Goes from -2 to +2, doesn't it? So could we write -2 and +2? Yes, but what's the other option? Could we double it? Why? Why can we double it? Because it's a beautiful symmetric interval, isn't it? So we could just go 0 to 2 and then double that. And I think that should be very doable. So basically, I want you to finish this one and try to do number 6 and 7. And you do have that program. And so that program has the ability to kind of take a look at a lot of these things. Go ahead and try to build it and see if you could see what they look like. And anyway, I guess I'm going to stop in terms of the recording there, but I'd like you guys to keep working on number 6 and 7. I do have answers. We'll throw those up in a little bit to see how you did.